So what I'm going to do first is I'm going to go through and look at the model summary. So you see the summary table for that B. So that node is on the dependent variable is what we're looking for here. So what we're going to see is we've got five things. The R square, the adjusted R square, the standard error of the estimate, and then what we generated out of the Durbin-Watson coefficient. And then it gives you the breakdown of all predictors plus the constant that we're going to see down here in the equation in a second. So let me walk through each of these. So the R here, what this means is it's the correlation between all observed and predicted values. What we have here is a R score of 0.499. R square is the how much variance your model explains. Where this is generated is it is the square of R. So R, big R here is nothing more than a correlation coefficient. It's giving you the total correlation as summed by the model itself. R square is nothing more than taking the square of 0.499 to give you a 0.25. What it's then going to do is it's going to take an adjustment to it. So what this is going to do is it's going to correct the score based on the number of predictors. If we see there's too much of a difference here between these two values, we might have something to be cautioned of, but we're pretty close. 24.9 versus 24.2. And I'll explain in a second how to interpret that. Next, we have the standard error of the estimate. So this is the average prediction error. So 0.8, so call it 0.83. And then the Durbin-Watson score here of about 2 on the nose, 2.03. So what this R is telling us, 0.499, is this is the multiple correlation between the observed and the predicted GPA. So a value of 0.499 means there's a moderate positive correlation between the predictors and GPA. So value of 0.5 is going to be a moderate level. So we feel pretty confident in the model's ability to show a linear relationship. But now to look at the model performance as we look for the R square. So what the R square is going to tell us is verbatim, 24.9% of the variance in first year GPA is explained by our models. So we can say this is an open interpretation. When this was originally published, there was a lot of interpretation about what's a solid score. And it really depends on how difficult your variables are to come by and whether or not we have something that's at a good predictive capacity. I would suggest that anything in educational and social science, when you've got a lot of outside variability that could be purely random by behavioral psychology or whatnot, that 0.24, about 25% of a model explanation is pretty solid. I wouldn't call it solid. I guess I would call it a comfortable. We can say that we have a pretty good model to work with. And then the adjusted R square of 0.242, so 24.2% shows the adjusted for the number of predictors to avoid overfitting. So it's slightly lower than the R square, but that's to be expected. Next, we have the standard error of the estimate. So this is what we're going to get out of this is the typical distance between the actual GPA and the GPA that's predicted by the model. So what we're saying here is that about on average, predictions are off by about 0.83 GPA points. And then finally, the Durbin-Watson statistic. I'm going to cover the assumptions here in a second, but this statistic tells us what we have in terms of autocorrelation for our residuals. We say that values between 1.5 and 2.5 are considered good. So since we have one that is at 2, which is right between the two values, we have no autocorrelation concern. We feel good about that assumption, but I'll come back to that in a second. So if we were to try to sum this up, what we would say is our model explains about 25% of the variation in GPA, which we would say is a meaningful amount of educational research. The predictors are collectively useful and the error is within a reasonable range of about plus or minus 0.83 GPA points. And then the residuals appear independent, which is how we would summarize that. The next natural step beyond this, and I'm going to get here in a second because I want to walk through item to item table in order that it comes, is to look at the assumptions that we're checking. So linearity, normality, homoscedasticity, and then multicollinearity. And I'll come back to those in a second here.